Greetings, digital architects and fellow travelers on the frontier of computation, and welcome to a technical deep dive that will fundamentally change how you view the machine sitting right in front of you. The question we're tackling today isn't what makes your computer run, but who is doing the heavy lifting, and why the ultimate partnership in modern technology is a symbiotic dance between two radically different processors: the seemingly familiar Central Processing Unit, CPU, and the revolutionary Graphics Processing Unit, GPU. This isn't just a comparison of hardware specifications, but a historical journey into the limits of general-purpose computing and the subsequent birth of hyperspecialization, a story that mirrors the very evolution of specialization in human society and industry itself. And I invite you now to join me as we lift the hood on this electrifying relationship to uncover why the CPU remains the essential, foundational brain, the steady hand guiding the ship, and why the GPU emerged, not as a challenger or a rival, but as an absolutely indispensable complementary force, an accelerator built purely for scale and relentless repetition. A story that has ramifications far beyond gaming, touching every facet of modern innovation from artificial intelligence to climate modeling. And we're going to trace every step of that evolution, setting the stage right now for a clear, structured breakdown that begins by establishing the bedrock of all computing. The foundation of nearly all digital existence, the CPU, has always been the uncontested master of the computer, the undisputed CEO of the system's operations, a sophisticated, highly optimized generalist engineered for maximum flexibility and sequential execution. And to truly appreciate its power and later, its limitations, we must look inside its intricately designed machinery, which is built upon three pillars of computational supremacy: the arithmetic logic unit, ALU, the control unit, CU, and cache memory. The ALU is the calculator, the workhorse dedicated to handling all logical operations, like checking if A is equal to B, and arithmetic work, addition, subtraction, multiplication. Essentially the engine room for every single calculation that keeps your software running. Its companion, the control unit, is the strategic commander, the traffic cop, whose singular and critical job is to fetch instructions from the main memory, decode them, and coordinate every single operation across the entire chip and system. It ensures that when you click a mouse, the resulting process doesn't collide with the background task of updating your operating system, maintaining a perfect low-latency order that is paramount to system stability. And finally, the essential and often overlooked secret weapon of the CPU is its cache memory, a tiny, but incredibly fast-access static RAM storage layer, L1, L2, L3, physically located directly on the chip, acting as the CPU's short-term memory, holding the data and instructions the core thinks it will need next, drastically reducing the time, latency, spent waiting for the slower main system RAM, DRAM, which is the absolute key to the CPU's dominance in executing single, complex tasks quickly. Because in the CPU's world, speed is measured in how fast it can respond to a single, critical command. The evolution of this architecture led to the introduction of multi-core CPUs, where multiple independent, complex processors, each with its own ALU, CU, and dedicated cache, were fused onto a single silicon die. An innovation that vastly boosted multitasking capability by allowing individual cores to perform entirely independent, sequential tasks concurrently. One core handles the operating system, another runs the web browser, a third streams a video, allowing the system to maintain its characteristic smooth operation and exceptional single-thread performance, making the CPU the ultimate foundation for all general-purpose software, managing everything from loading the operating system itself to executing high-level application logic. This CPU architecture, brilliant as it was for general-purpose computing and sequential task handling, began to reveal a critical structural weakness as the demands of computing evolved beyond simple command and control logic. And the story reaches a critical tension point in the late 1990s and early 2000s. The advent of complex, real-time graphics and 3D animation workloads, particularly driven by the insatiable demands of video games. This new computational frontier demanded something the CPU was simply not engineered to deliver: massive, simultaneous repetition. Consider the task of rendering a single high-definition 1080p frame, which contains over 2 million individual pixels, and in a video game, this frame must be calculated and displayed 60, 90, or even 120 times every single second. meaning the system needs to perform hundreds of millions of complex shading, lighting, texture mapping, and geometric calculations in under a second. A workload that is inherently highly parallel because the calculation of one pixel's color and depth is completely independent of the calculation for the pixel right next to it. The traditional CPU, built with a few highly complex cores designed to excel at making sequential, strategic decisions, like what is the next instruction, and prioritizing low latency, found itself completely overwhelmed when forced to handle this brute force visual computation, trying to process millions of simple, repetitive pixel-by-pixel calculations one after the other in a strictly ordered, sequential manner, spending valuable time managing the logistics of the calculations instead of simply executing them, proving that traditional CPU design was profoundly insufficient and inefficient for the monumental task of heavy, highly parallel visual calculations, marking the undeniable moment when a dedicated, specialized computational accelerator became not a luxury, but an absolute necessity for the future of visual computing. Out of this computational crisis, the narrative pivots dramatically to the birth of the Graphics Processing Unit, GPU, a component engineered specifically to resolve the CPU's graphical bottleneck and built fundamentally to handle visual rendering at an unprecedented scale. The GPU mirrors some basic structural elements of the CPU. It still has Alice to perform math, but it distinguishes itself through a radical philosophical departure in its architecture, moving from the CPU's paradigm of fewer, smarter cores to a new paradigm of many, simpler cores, where a high-end CPU might feature a handful, 4, 8, or 16, of large, complex, and deeply managed cores with massive caches and powerful control units. A modern high-end GPU boasts an enormous array of specialized ALUs, often grouped into hundreds to even thousands of tiny, streamlined cores. NVIDIA calls them CUDA cores, AMD calls them stream processors, all packed onto a single die, creating a silicon machine that is an unparalleled factory of parallel processing. The fundamental brilliance of the GPU is that it excels not by being individually powerful or by making complex, quick decisions, but by sheer simultaneous parallel capability. It sacrifices the CPU's set flexibility and individual core speed for the ability to execute the exact same instruction on thousands of different data points, thousands of pixels for instance, at the very same microsecond, prioritizing throughput, the total amount of work completed per unit of time, over the CPU's low latency focus, essentially transforming the CPU's small expert team into a massive, highly efficient assembly line where every worker performs the same simple task simultaneously, finally solving the graphics problem by dedicating a single specialized component to handle the repeatable, heavy lifting of visual calculations. The story of the GPU might have ended there, confined to the niche of graphics and gaming, but the sheer power of its highly parallel architecture initiated a pivotal world-changing turning point in the mid-2000s, leading to the profound realization that the mathematical engine powering visual rendering was fundamentally the same engine required for other, computationally intensive tasks, allowing GPUs to evolve far beyond their initial purpose as mere graphics machines. The key was recognizing that rendering a 3D scene, performing millions of parallel matrix multiplications to calculate lighting and geometry, used the same underlying linear algebra operations required for a vast array of scientific and data-driven workloads, opening the floodgates to entirely new domains. Their natural strength and parallel repetition made them indispensable in fields such as machine learning and deep neural network training, where billions of small, repetitive multiplication and addition operations are needed to adjust weights. Financial simulation, running thousands of complex risk models simultaneously. Scientific workloads, simulating fluid dynamics, molecular modeling, and particle physics. And, most critically, powering the rise of modern artificial intelligence, AI. The GPU transitioned from being a visual specialist focused on making dragons look real on your screen to becoming the indispensable computational powerhouse driving the next industrial revolution, capable of accelerating tasks that would take traditional multi-core CPUs days or weeks, allowing researchers to train models like GPT-4 or analyze vast genomic datasets in previously unimaginable timeframes, essentially offering a shortcut to previously intractable computational problems by embracing mass parallelism. This history brings us to the present day, where the comparison intensifies with the direct, architectural and functional contrast that defines their roles. The CPU and GPU are the ultimate specialized partners, each excelling in its clearly defined domain. The CPU is primarily designed to handle general sequential tasks. Its architecture places a premium on low latency and fast, complex instruction execution, running the operating system, managing I/O operations, controlling all peripherals, and executing the core program logic sequentially, making it a powerful sequential manager with few complex cores, optimized for single-thread speed. Conversely, the GPU is designed to handle highly parallel execution. Its architecture prioritizes throughput above all else, using its vast array of simpler cores to process multiple data points simultaneously, making it an extraordinary parallel accelerator, optimized for maximum concurrent execution. Their use cases diverge perfectly. CPUs run all aspects of everyday computing: opening a document, browsing the web, loading the operating system, running the complex, non-repeatable core logic of an application tasks that require quick decision-making and precise sequential steps. Meanwhile, GPUs dominate high-performance, repetitive, mathematical tasks, rendering millions of triangles in a game, training an AI model on millions of data points, or mining cryptocurrency tasks where the same instruction is applied across a massive dataset, proving that while both are processors, one is built for depth and management, and the other for sheer, unadulterated scale and speed of repetition. The story concludes with the most critical and unifying message of all. The GPU does not, and likely will not, replace the CPU. Instead, they exist in a state of synergistic enhancement, defining the modern paradigm of heterogeneous computing. The CPU is, and remains, the master of the system, the central orchestrator that manages the main program logic, executes the operating system, handles communication, and decides when a task is repetitive enough to be offloaded. The GPU, the dedicated worker, accelerates those repetitive, parallel calculations under the CPU's direction, returning the final process result back to the CPU for the next sequential step. The fundamental distinction, sequential versus parallel processing, is the core truth of this partnership. Without the CPU, the GPU is an engine with no driver or map. Without the GPU, the CPU is forced to use its generalist skills for specialized, massive tasks, crippling the entire system's efficiency. Therefore, the true insight for all of us is that maximum performance in modern computing is achieved not by building a better generalist, but by perfect specialization and strategic delegation. It's a harmonious relationship that underpins the complexity of everything we do digitally. And I hope this deep dive has reinforced that fundamental distinction between the critical sequential manager and the unstoppable parallel accelerator. Now, having explored the silicon partnership that powers our world, let's take a moment to reflect on the lesson for ourselves and the advice we can draw from this technological evolution that can easily be applied to our daily lives. The core lesson is the profound power of specialization and strategic delegation. Too often in life we try to operate as a singular, highly complex CPU, attempting to handle both the high-level strategic sequential decision-making, like career planning, managing relationships, or learning a complex new skill, and the massive, repetitive brute force tasks, like organizing files, sorting emails, or drilling practice, all on our own complex sequential mental core, leading to burnout and massive inefficiency. The advice I draw from this is to identify the GPU tasks in your life, those things that are repetitive, require high throughput, and are simple in their individual execution, and find ways to delegate, automate, or dedicate a specific, focused GPU time to them, freeing up your mental CPU cores for the high-level, sequential, complex decision-making, the creative problem-solving, and the deep, low-latency interactions that truly require your unique, complex human intelligence. By consciously separating your sequential, decision-based workload from your parallel, repetitive workload, you achieve far greater throughput in your life, unlocking exponential efficiency just like the modern computer. I encourage you to ask yourself this thought-provoking question for your own reflection and interaction in the comments below. Where in your own life are you using a complex, sequential CPU-like approach, worrying, overthinking, or trying to manage details, when a simple, dedicated parallel GPU-like approach, automation, batching, or focused repetition, would unlock immediate, exponential speed and reduce your mental latency? Let me know your thoughts and your own personal CPU-GPU breakthroughs. Finally, I want to send you all my warmest wishes for good health and boundless mental energy as you navigate your own computational challenges. And if this journey through silicon strategy has sparked your curiosity and added depth to your technical knowledge, please do me a great favor. hit that like button, share this video with a fellow tech enthusiast, and most importantly, subscribe to the channel and ring that notification bell so you never miss another deep dive into the fascinating world of technology and beyond.